Hi guys, this video is brought to you by Academy of Higher Learning. Please visit our website at aohl.info to view more videos like this. In this video, we will be talking about limits and continuity. So pretty much going over the concepts. So the first thing I want to talk about is the notation for limits. You probably have seen it somewhere. It's something like this. So it's limit, or lim for short, x approaching some random value for the function of f of x equals, say, L. So what does this mean? This basically means that as x comes closer to a, f of x, or it comes closer to value y equals L. So that's what it basically means. But for limits, if you look at it in a graph, there are, so like I'll draw an example. Say we have a function. This is a function, and we want to find the limit of this point a. So as it's coming closer and closer to this a, the y value is getting closer and closer to L. So as you can see that we can take limits from two sides, the left side, and the right side. So we can divide this up into two sides. So when dividing it up, what we do is this is how we write if we want to look at the limit on the left side. So x approaches a minus, this indicates that it's from the left side, f of x equals L. And to indicate if it's from the right side, instead of having the minus, we have the plus. So this indicates it's on the right side. Now when the left side and the right side equal, or the equal like the same number or same value, we can say that the overall limit, which is this one, exists. So therefore, since in this case from the left side it equals L and the right side it equals L as well, we can say that the overall limit, which is x equals a, f of x, and the overall limit exists and it equals L. So that's what it basically means. Now, some of you might get confused and say that, oh, well, if can the limit x approaches a, f of x equals L, is it the same thing as, like, say, at f at a? Well, it's not always the same. The function value at a will not always exist or will not always be the same as the limit. Therefore, we cannot, like, say, conclude that these two are equal. But in some cases, they are. And in addition to that, like, limits, when finding it, we can, like, say we have a rational function, we can, like, factor it and try to take out common numbers and then solve for the limit. Whereas when finding the value of a function f of a, we can't do that. So you have to keep that in mind. However, if the limit, if these two equal or the same, then we can say that the function, or f of x at x equals a is continuous. Only if the overall limit equals the function value. Therefore, we now come down to, like, the conditions. So basically, you guys must have, like, figured out by now. In order for a function to be continuous, like I said again, the function value has to exist. If it doesn't exist, then it's not going to be continuous. Second condition is that the overall limit must exist. And in order for the overall limit to exist, the left-hand side limit must equal the right-hand side. This is important as well. And last condition is that the overall limit should equal the function value. So say we don't have, like, one of these conditions is not satisfied, we will get a discontinuity. So a discontinuity is when there's either, like, a chump, or the function is not continuous. Basically, pretty much, it's not like a smooth line. There's, like, either a hole in the middle, or it's like something like this. So this is some kind of discontinuity because there's a chump. So you probably have seen that somewhere. And there are a bunch of discontinuities. There are three discontinuities actually. The first is chump, and the chump discontinuity can be described, like, can be split into two. So the first chump discontinuity is, say we have a function something like this, and we have a line, pointer, So something like this. So this is the function f of x. Now, if you want to take, if you want to see if it's continuous at point a here, x equals a, well, the function value does exist, which is this value. The overall limit does not exist because the left-hand side limit equals to, say, this is b and this is c. So the left-hand side equals b, whereas the right-hand side equals c. Therefore, the overall limit does not exist, and which concludes that the condition 3 is automatically is not satisfied. Therefore, when there's a jump discontinuity, this type of jump discontinuity occurs when condition 2 is not satisfied. Missed the E. Okay. So there's another type of jump discontinuity. Say we have a case something like this. We have a graph and it's a hole here and it's a hole here and it goes on. And this is A, this value is B, and again this value is C. So in this case, it's not the same thing as this. Well, it may look like the same thing, but it's not. Why? Because we have holes. Therefore, condition 1 is not satisfied. F of A does not exist. Neither does the overall limit, because the left-hand side equals B, whereas the right-hand side equals C. Therefore, neither of the conditions are satisfied. Therefore, conditions 1 and 2 are not met. But the second type of discontinuity is infinity discontinuity, and you probably have seen this before, like bunch of times in your early grades when graphing functions. And this type of discontinuity is self-explanatory. It's something like, say, we have a case like this. So it's a bad, y-axis are kind of crooked, but as you can see that it's going to infinity. From the right side is going to positive infinity, and from the negative side is going to negative infinity. And this is the same case where when something goes to infinity, the limits do not exist because infinity is not a defined value. Therefore, condition 2 is not met, nor is condition 1, because it's going to a value, but it's not going to a specific value. Therefore, condition 1 is not met either. Therefore, we can also get infinity discontinuity. So when condition 2 and 1 are not met, it could be either jump discontinuity or infinity. So you have to keep that in mind. Make sure that it's not infinity over jump or vice versa. The third type of discontinuity is removable discontinuity, and this can occur two ways as well. The first way is, say we have a case something like this. Say we have a graph and it's going like that, and there's a hole in the middle and keeps going. Now, as you can see that the left side limit, okay, this is point A and this is B. So as you can see that from the left side the limit is approaching value B. So is from the right side. Therefore, the overall limit does exist, and that is B. However, the function value at A does not exist. Therefore, condition 1 is not met. I forgot not. Okay, and the second way this can occur is basically by having something like this. It's a similar case, and say you have a function like this. This is value B at A, and there's a value this, and this is C. So we have a function like this. In this case, the left side and the right side limits do exist. However, and so does the value at f of A. F of A equals C, and the overall limit equals B. However, the condition 3 is not met. As you recall, the condition 3 is where the overall limit should equal the function value, and in this case it does not. Therefore, condition 3 in this case is not met. It's not met. So these are the three types of discontinuities. So now let's do a little example. So say we have something like this: f of x equals x over x plus 1 squared. So now there are two parts to it, a and b. First I have to check if it's continuous. So let's try to do the first condition. First condition is, does the value exist? So if I put in f minus 1, will I get a value? Well, let's see. At the top I'll get minus 1, but at the bottom I'll get 0. Therefore, a number over 0 is not a defined number. Therefore, it does not exist. So now we know that it's not continuous, so we're done this part. Let's go to B. So what kind of discontinuity is this? So let's go to number 2. Let's take the limits. So if I take the limit from the, say, the left side, minus 1, f of x. So this is f of x, I'm not going to write it. So as you can see that this is going to be negative 1, and this is going to be approaching 0. So therefore, it's going to be approaching negative infinity. You can do the approach test yourself, but it's kind of like you can see by looking at it there. And from the right side, it's going to be the same thing. It's going to be approaching negative infinity. Right side. Therefore, since it's approaching infinity, we can technically say that the limit as x approaches negative 1, f of x approaches negative infinity, but the limit does not exist. Therefore, condition 2 and condition 1 are not satisfied. And as you can recall, since it's approaching, we cannot say this is a jump discontinuity because it's approaching infinity. And we can even look at the graph to even prove that. So if you have negative 1 here, it's going to be approaching infinity, negative infinity from here, asymptote here. Oh, that's bad. Sorry, the graph is pretty bad, but you guys can see the point that it's approaching negative infinity at x when it's approaching negative 1, x equals negative 1. And we can say that this is an infinity discontinuity. Not not jump, I mean, but infinity. So let's do another example and try it yourself. So pretty much pause the video or something like that because I have the answer in the next page. So I'm just going to keep it open for 5 seconds. So in this case, you're trying to find the if it's continuous, same thing as before at x equals 2, and what type of discontinuity is it. So now I'm going to reveal the answer. So this is the answer. I'm just going to go over it pretty fast. So f at 2 does not exist, and the limits do exist because the left side equals the right side, and the overall limit is 3. However, it's a removal of discontinuity because condition 1 is not met. So because the function value does not exist. Thank you for listening, and hopefully you guys learned something new. And check out our more videos or visit our website aohl.info. Goodbye.